All right, lesson 2 of chapter 24. One thing I wanted to start out with in this lesson is just kind of a reminder of where we came from in chapter 23 to where we're now in chapter 24. So what you're seeing right here for number 1 is basically what we did in chapter 23 with our process of limits and doing the limiting process for finding an instant rate of change, and how we now have a shortcut in doing this. So here was a typical problem from chapter 23. We were given a function like this, and ultimately what we were looking for was the instant rate of change, or the gradient, at x equals 2. And so in order to do that, we said, okay, well, let's develop this process where we do a 2 and a 2 plus h, and go through this whole process of working with gradients from 2 to 2 plus h, so that we could develop this expression that we had here. And we'd say, okay, well, now the limit as h approaches 0 is 2. And so we came out with this gradient of 2 when x equals 2. Well, that was quite a lengthy process in order to get this gradient at x equals 2. So here we are now in chapter 24. Instead of using the limiting process to get this information, we can now use our knowledge of derivatives and the power rule in order to accomplish the same thing, but much quicker. If you look at this function that you see here, we now look at this and we say, well, what's the derivative of f prime of x for that same function? Right? And we say, well, using the power rule, we would do 2 multiplied to the front, subtract 1 from the exponent. Same thing with my second term. 1 times negative 2 is negative 2. Subtract 1 from the exponent, and we get this derivative. And now all we have to say is okay, well, what's the gradient when x equals 2? And so we take our 2, we sub it in for x right here. 2 times 2 is 4, minus 2 is 2. So we'd say the derivative, or the gradient, at 2 is 2. And so we get the same answer that we got with the limiting process, but so much quicker and so much less work. So this became a much more efficient process with the use of derivatives instead of the limiting process. But it's the limiting process which is why this process works. So you now have kind of the background, a little depth of knowledge here for where derivatives come from and why they work. This just is so much more efficient that moving forward, this is the only process that we're going to be using. So one thing I wanted to remind you of with that example is when you work with derivatives, remember it is gradients or slopes that you are working with. So when we take the derivative of at 2, where x equals 2, we're getting the slope of a function where x equals 2. So this is the gradient, or the instant rate of change, for this function when x equals 2. And so looking at a similar problem right here in number 2, now working with derivatives to accomplish that goal. Again, they're now asking us for what is the gradient when x is 3. And again, in the past we would have said, well, let's do 3 and 3 plus h and go through that whole process and find the limit as h approaches 0. But now working with derivatives, we can just say, well, let's just find the derivative and sub in a 3 for x. So we're now going to say, okay, let's find the derivative of that function. So let's just start with the general derivative for that. There we go. With what we did in lesson 1, that would now mean using the power rule, we would have 3x squared minus 4x to the first. Our constant goes away. So we'd say, okay, well, here's the derivative. So now if I plug in 3 into that derivative, then I can now get the gradient, or the instant rate of change, when x equals 3. And this is so much quicker than doing that limiting process. So if we do a little cleanup on that, 9 times 3 is 27. 27 minus 12 is 15. And that's our slope, or gradient, when x equals 3. So do keep in mind that whenever you are working with a derivative, the result that you get is a slope, or a gradient. It is not a coordinate. It's not an x coordinate or a y coordinate. It is simply a slope, or a gradient. The x coordinate was 3. The slope is 15. All right, so Going on to number 3 here. Similar idea, we're still looking for the gradient. Anytime you see the word gradient, you can immediately replace that with the word derivative. So that's like saying find the derivative of the curve at this point. And so if I know that my g of x function looks like this, we can use our power rule and get g prime of x, or the derivative, using our power rule. So we'd be looking at 9 minus 3x squared for the derivative. And so now if they say, okay, well, what's the slope at this point on the curve? Well, which one of those points do we need? Right? It's the x coordinate that we always sub in order to get the gradient at that point. So we can now do g prime of 2, because 2 is the x coordinate. So this is what our setup will look like. So we subbed in our 2 into the derivative. If we do a little cleanup on that, 4 times 3 is 12, 9 minus 12 is negative 3. So we can now say that at this point, the slope, or the instant rate of change, or the gradient, is negative 3. Ultimately, where this is going, let me just throw this out there, what we're going to be doing is writing the equation of a line. And remember, to write the equation of a line, you want a point and a slope, so that you can do point-slope process to write the equation of a line. And so that's where all this is headed. But in this section, we're just working on developing the point and the slope by using our derivative. So going on here to number 4. So determine the coordinates where the gradient is 11. So now in this case, let me show the last one real quick. So in this case, we are now given this information, and we're asked to find this information. So we know the derivative, and they're asking us to figure out the x coordinate and the y coordinate that occur at this gradient. So here is our function. We know the slope, or the gradient, is 11. We need to come up with the coordinates at that point. So we still want to work with a derivative, of course. So we have the original function up above. Here is the derivative based on the power rule. So we're looking at 3x squared minus 1 would be the derivative based on our power rule. Well, in this case, we don't have an x to sub in. That's what we're trying to find. We know the gradient is 11. We know the result is 11. So now in this case, I'm going to set the entire function equal to 11, equal to the gradient, so that I can solve for the x coordinate. So if I add my 1 over, and then divide by 3, and square root both sides, I get plus or minus 2 as my x coordinate. So there were 2 points on this curve where the gradient was 11. So looking at those, we know that I have 1 point for positive 2 for x, another point for negative 2 for x, and now I just need to come up with their y coordinates. So there are 2 different locations that had slopes of 11 for this problem, so for this function. Well, how do you ever get a y coordinate? You take an x coordinate, you sub it into the original function to get a y coordinate. So if I take my 2 and sub it in right here for x, so 2 to the third minus 2 plus 2, right, and we get 8 is the y coordinate. One thing that I always want you to keep in mind for these is, where do you get a y coordinate from, and where do you get a gradient from? In both cases, we are using an x, right? But the result that you get comes from 2 different functions. So anytime I sub in an x coordinate into the original function, I get a y coordinate. Anytime I sub an x function into a derivative, I get a slope. So keep that in mind. It's where you plug in the x determines what kind of a result you get. From the original function, you get a y coordinate. From the derivative, you get a slope. And so keep that in mind. 2 different uses come from that same x coordinate. In this case, again, I'm looking for another y coordinate. So if I take my negative 2 and sub it back into the original function, since I'm looking for a y coordinate, so negative 2 to the third is negative 8. Negative 8 minus negative 2. So that's like saying negative 8 plus 2 is negative 6. plus 2 is negative 4. So we had two different locations on this function where the gradient was 11. Something to always consider is you always have to read the directions very carefully because there are subtle differences within those directions. This one specifically said the coordinates, so I needed these ordered pairs. I needed x's and y's. Some just say find the x coordinate, and so all you would do is you'd stop right here and just list the x coordinates. So it's a matter of reading carefully. If they say find the x coordinates and you give this as your answer, you would be marked off for that because that's not exactly what they were looking for, right? This is what they would be looking for. But in this case, they said find the coordinates, so we did come out with the full ordered pairs to do that. All right, last one for this lesson. Given that function, another cubic function, find the coordinates. So again, I'm looking for ordered pairs on this one of all points that have a horizontal tangent. Well, what does that mean? If they have a horizontal tangent, what do we know about horizontal lines? Well, we know that the slope of any horizontal line is 0, right? The slope of a horizontal line is 0. So that is their way of telling us that we have a slope of 0. So in this case, again, of course, I'm going to be working with a derivative here. That's the theme of the chapter, so let's just start with that. So if we take our derivative of this function using the power rule, we're going to be looking at 3x squared minus 2x minus 1. So there's our derivative. So let's see what we're looking for here. So ultimately, I want coordinates. And so I'm going to be looking for some ordered pairs. I don't really know how many yet. It just says all the points. So I know that's kind of ultimately what I'm looking for. So to do that, let's just take our given information. This is the only thing we know at this point, is that the slope is 0. Well, remember what that tells you. If the slope is 0, that's like saying your derivative is 0. So I'm going to set this whole thing equal to 0 so that I can figure out the x coordinates to go with that slope of 0. A common mistake made on this type of problem on our test or in any test situation is students automatically want to sub in a 0 right here for x. Well, keep in mind, this is not an x coordinate. It's a slope. So the only thing that goes in for this x or this x is an x coordinate. So that's all you could ever sub in for those, not a slope. The slope is the derivative, so I'm setting the whole thing equal to 0 in order to figure out the x coordinate. Anyway, if we go on to solve that equation, obviously we're solving a quadratic equation here, so you can either solve that by factoring or quadratic formula or with your graphing calculator. Any of those methods are good. I'm going to go ahead and factor it. So in this case, my two factors, if I were to go through factoring on this, would be 3x plus 1 would be one factor. The other factor would be x minus 1. So based on those factors, I can see that x would equal, based on him, if I set this equal to 0 and solve for x, I get negative 1/3. Based on this one, I get a positive 1. So there are 2 points on this curve where the gradient is 0 because I have horizontal tangent lines. So we now know the x coordinates, and because this problem specifically said find the coordinates, I now need y values to go with those to create the ordered pairs. And remember, where do you always get a y value? From the original function. So the derivative will always give you a slope, but the original function will always give you a y coordinate. So if you take negative 1/3 and sub it in for x into the original function, we are going to get a 32/27 result from doing that. And obviously that's something you could do on a calculator, so that's a bit of an ugly fraction, but some easy calculator work would take care of that for you. For the other guy, if I sub in a 1, this one will be a little easier. If you plug in a 1, you come out with 0. And there you go. Those are the 2 points on this function where you would see horizontal tangent lines. I'm going to show you one quick example of where that comes from in your calculator and how you know that works. So let me just give you sort of a graphical representation of what we just found out here. So if I go to my graphing portion here, let's plug in the original function. So x to the third minus x squared minus x plus 1. So if we were to graph that, let me see if my window's okay here. There we go. So there's our cubic function. Well, where would we find zero slopes? So if you think about what we've talked a little bit about in the past on this idea, as you see right here, all the slopes in this part of the graph are positive. Because if I were to start drawing lines here to connect to those points, tangent lines, these lines would all be going in the positive direction. Well, right here as you start getting towards the top, right there at that point, if I were to draw a horizontal line, I would have a zero slope. So then I have a zero slope, then it goes into the negatives. So in this area I have negative slopes. In this area I have positive slopes again. Well, what happens in between negative slopes and positive slopes? You have to pass through a zero. So we have a zero slope at this minimum. I have another zero slope at this maximum. So those are my two zero slope locations. And those points are those points. So watch what happens on this graph. I'm going to zoom in really quick just so you can see this. Let me zoom in on this area of the graph. Make it stand out a little bit more to you. There we go. So obviously he stands out right away. 1, 0 is clearly the minimum right there. And to do that, if I really wanted to, I could go under Calc and choose minimum. And I could use the minimum feature to find that point, which is that point. If I went under Calc and chose maximum, I could get the coordinates of that point, which we found right here. And so that's an option too for getting those maximum or minimum points, which would have a slope of 0. Well, watch what happens if I draw in a tangent line to go with this point right here. So if I plug in 32 over 27 and graph that, well, there you go. See the tangent line right there at that maximum point, right? It's a horizontal line, so it has a slope of 0, and it's hitting right there. If I graph y equals 0, I'm going to get my other tangent line going through right there. So if I go back to this and I graph y equals 0, I don't know if this will show up. There it is. Goes right through that point on the graph. So yeah, so for that's why these 2 points have 0 slopes for their tangent lines if we were to graph those.